Yeah.
Hi everyone, and I welcome each one of you once again to the Pi seminar series dedicated to advancements in scientific machine learning. Today we have with us Dr. Chris Rackauckas, who is the Vice President of Modeling and Simulation at Julia Hub, the Director of Scientific Research at Puma's AI, co-PI at the Julia Lab at MIT, and the lead developer of the SciML open source software organization. For his work in mechanistic machine learning, his work is credited for 1500x acceleration of NASA launch services, simulations, and recently demonstrated a 60x to 570x acceleration over Modelica tools in HVAC simulation, earning Chris the US Air Force Artificial Intelligence Accelerator Scientific Excellence Award. He's the lead developer of Puma's project and has received a top presentation award at every ACOP in the last 3 years for improving methods for uncertainty quantification, automated GPU acceleration of nonlinear mixed effects modeling, NLME, and machine learning assisted construction of NLME models with deep NLME. For these achievements, Chris also received the Emerging Scientist Award from ISOP. And today's talk that Chris will be giving us is going to be on the topic enabling industrially robust AI for engineering through scientific machine learning. And in today's talk, there will be more focus and emphasis on methods that can guarantee accuracy. At the same time, will also have the ability to quantify that uncertainty. And there will also be some focus on the demonstration of these methods or models to applications such as two-phase flow for HVAC systems and even for lithium-ion battery packs to showcase the improved robustness of these approaches over standard scientific machine learning architectures. So over to you, Chris, for the rest of the talk for today's session. Thank you.
Yeah, thank you very much. And yeah, I hope we'll be able to get through all the different topics there, but we'll see what's all able to be hit.
Sure.
Yeah, so I definitely from the introduction, you should be able to tell that one of the differences I might have from a lot of purely academic folks is that I've been involved in a lot of industry projects. I've had a startup that, and I'll mention actually both of these as well. Startup in pharmacometrics and now a startup in industrial modeling and simulation. Both have grown to over 100 employees post Series A and all this, where scientific machine learning has been a pretty essential part of the software products that it had been developing, right? So what I want to kind of discuss is, like this, I want to discuss the scientific machine learning, which, I think is something that for this group, a lot of people might already know a little bit about, right? But I want to kind of discuss scientific machine learning with this kind of hat on or the standpoint of what's actually required to make it so that way it works in an industrial robust setting, right? Because yeah, it's one thing to be able to make a physics-informed neural network be able to be trained on your computer and you use it for a paper, right? That's like, the thing that you do as a student and as an academic, right? But it's another thing to be able to say, okay, now this is something that's good enough where, in a graphical user interface where someone knows nothing about machine learning, can they just click a button and then just expect this to work? And I think if most people have,
那大概拍到有可能会有这个问题。然后
and I think that most people who have, say, used scientific machine learning packages or played with physics-informed neural networks at this point probably know that, like, oh, just click one button and make it work is not necessarily been the goal of, like, a lot of the papers that you see out there, right? They're fine-tuned in terms of how they're doing the training and such. But if we really want to make this so that way this is something that is robust and translatable beyond requiring that everyone has a PhD and spends 5 years on their PhD project for this, right? How do we make this so that way it's as simple as, say, hey, I use an ODE solver, I use ODE 4 or 5 from MATLAB, and so therefore just solve the equation, right? Like what is required to make it go to that level? Um, so just to make sure that we're all in an even playing field, what is scientific machine learning? Right? Scientific machine learning is model-based data efficient machine learning. And the idea is that instead of just using data, right? Google size data, 3 billion rows of, here's all the data that I have, train machine learning to be able to reproduce exactly what you get from the data set, right? In a lot of scientific cases, you do not have a good data set that you can train that on, right? You don't have a corpus of text throughout the entire internet for something like, say, general relativity, right? In fact, for general relativity, you don't really have all that much data. It's kind of a surprising thing to think about because it's such a well-known and tested theory. But if I was to ask you, what is the 1 billion row data set that you would use to train an AI on, such that it will always get, all behaviors of general relativity correct? You'd actually be pretty hard pressed to find one. In fact, I don't think you can, because the way that we've been able to find out that a lot of scientific theories are correct is actually through what's known as heterogeneous data, right? So heterogeneous data is different, So when you think about homogeneous data, right, you think about something like, the text of Wikipedia, right? You know, all of the text is in the same file format. It's all in the English language. I mean, okay, there's other language ones, but thinking about the English language Wikipedia, there's all this English language text, and even if you scrape a whole bunch more websites, you still have all the same type of data. It's all homogeneous data, right? But a lot of scientific theories and a lot of scientific knowledge comes from heterogeneous data, right? So how do you know that general relativity is correct? Well, one proof of the general relativity is correct is because remember Sir Arthur Eddington's proof that when you look at the solar eclipse, you see that the stars actually move, right? There's the gravitational lensing experiment. There's gravitational lensing around certain galaxies. There's the perihelion of Mercury, right? The non-elliptic movement of the planet Mercury around the sun is one major point to be able to show general relativity's predictions. The change of timing on satellites, GPS satellites have to be change their timing in order to account for relativistic effects, right? All of these different effects are all points to be able to say, hey, we know that relativity must be at least approximately true because I have this piece of data here, this piece of data here, this piece of data here, this piece of data here. So therefore, this equation, right? But there's no billion row data set that you can point to for a lot of scientific phenomena. So I think one of the things that people kind of miss a lot when kind of talking about scientific machine learning is that one of the real use cases here is that, our scientific knowledge and scientific equations capture what is really true and what is preserved across many different scales, multiple scales and multiple phenomena with the things that we see heterogeneously through many, many, many different types of experiments. Right? Not just one experiment with a lot of data, but also lots of experiments with little data. And so what we want to be able to do is we want to be able to build prediction pipelines that are not just focused on the Google problem of I have this huge giant data set, but they also should be focused on the scientific problem of, I have 20 data points from, perihelion of Mercury. I have 20 data points from this gravitational lensing. So therefore this equation is correct. And let me use this equation that I've been able to generally show is correct let me use that as a foundation as part of my prediction engine, right? And so scientific machine learning is this idea that we don't need to just do mechanistic modeling and we don't need to just do data-driven modeling. We can do these types of methods, which is using the knowledge of both of them in tandem and weighing the pieces that we know to properly, right? And it's kind of running under this assumption that, the way to make a good prediction is that you're really just trying to pour enough prior knowledge into there, right? You can pour in knowledge in the form of data. You can pour in knowledge in terms of, known equations that you expect to be correct, right? But it doesn't matter which one you're pouring in, as long as you pour in enough knowledge, you should be able to get a good enough prediction. So how do we get these methods that are able to use the two sources of knowledge interchangeably? And the core point really then is that, the structure that is encoded into the model, like the more structure that is encoded into the model, the less that you need to learn from the data. And so therefore, the more data efficient it is. And let me kind of get through this point first before going into a lot of the robustness aspects. So a lot of the scientific machine learning that we do are what's known as these universal approximator differential equations, or you cut this short to universal differential equations, right? So what do I mean by this? Well, so the core point is that, the property that we want for machine learning is really just that, these machine learning architectures are universal approximators, right? They are objects that are able to approximate every possible function. In a mathematical sense, what you say is, for all functions Rn to Rm, which are, say, continuous or some sufficiently nice space, then there exists a set, a size of the neural network. So enough layers, enough size of the hidden layers, such that this neural network is able to approximate, any given function epsilon close over this whole compact domain, right? You're able to make that statement be very rigorous, but all that's really saying is that if you give me any sufficiently nice function and you make your neural network big enough, this neural network will be able to approximate that function. And so what we use this for is to be able to turn the problem of trying to find functions, which is an inherently discrete problem, right? Oh, am I missing an x squared? Am I missing an x cubed? Am I missing a sine x, right? This problem that is inherently a discrete search problem, turning that into a continuous search problem that is, optimize these parameters of a neural network, right? Parameters of a neural network are basically, you can think of it then as a smooth continuous approximation to the search problem of finding a general function expression. Right. And so how we use it then is as follows, right? So if if let's say you have a case like here, we have the partial Lockyer equation, where you say, okay, the number of rabbits, x prime grows exponentially. If you leave rabbits in a room all on their own, they grow exponentially. And if you leave wolves all alone in the room, well, there's no food source, they'll have to eat each other, and so there's exponential decay. But if you put rabbits and wolves in the same room together, they will probably have some kind of interaction. And so here's the model that I'm presupposing, and the things that I don't know how to write down, I'm just going to capture the neural network, right? And why is this a valid formulation? Well, because again, this comes from the universal approximator theorem, right? Technically, this is all possible functions, right? Every single function you can ever write down, you can just say, hey, it's a neural network, just find the right weights for the neural network, right? And so what we're doing then is we're just saying like we're using this to be able to write down the pieces of the model that we weren't able to do, right? And now what I really want to talk to you about, what I really want to show at first here is that adding this bit about the piece of the model that I know is actually very helpful for actually making sure that this is working correctly, extrapolating correctly, and doing well, right? So the point then is that you can do everything with a neural network, but the more you force that neural network to be doing the work, and the less prior knowledge you have here, then the more data that you have to effectively have to do in order to make this work out well. And so, I like to do this as a step-by-step process. So let's start with just standard machine learning. So, here's a neural ODE. U prime equals a neural network, right? So basically what this says is, all possible ODEs that fit the data, right? And so what we do then on this case is this is a case that I'm looking at the first 21 days of the COVID-19 pandemic with the in the Wuhan province region. And what we want to do is we want to say, can we predict that a pandemic is going to start, right? Or can we predict what the motion or the growth of the pandemic is, the growth speed, right? From just the first 3 weeks of data. And so here, from 0 to 21 days, you can see this is where we stop training. You can fit the neural network here, but then you don't necessarily extrapolate well with the neural network, right? And so a lot of people will say that, this is because, people give like these bullshit high level, they'll say like machine learning doesn't extrapolate, right? It's like, no, let's that is true, but let's actually be a bit more accurate in what we're saying here, right? So remember, the purpose of a neural network is to be it's a universal approximator, right? And so what we're basically saying in this sense is find out of the space of all possible functions that fit the data, find one possible function that fits this data, choose one function randomly that fits this data and extrapolate, right? And it happened to choose one that didn't extrapolate well. In fact, it doesn't have exponential growth, yada, yada. It doesn't have a lot of the properties that we'd expect of an epidemic. And the point is not that, the machine learning doesn't extrapolate well. It's that we underdeclared the problem, right? We said find any possible function that fits the data. And it did exactly what we said, right? If you think about the mathematical formulation, this did exactly what we said. We said find any possible function that gives me an ODE that fits the data. It found a pretty good one. And then we say, oh, but you didn't do this. Well, how it extrapolates wasn't in the problem description at all. So of course it didn't find anything to do there. Well, there, right? I mean, out of probabilistically, it could accidentally find the right function, right? But there's nothing that would drive it in the right direction. So then the real question is, can we change our problem formulation such that we are better guaranteed to be able to have it so that way it works out and extrapolates in a way that we would expect a pandemic to extrapolate? Right? Well, one way to do that is to be able to use the phenomenological forms that we know from pandemic modeling, right? So here, for example, is then the first version of our universal ODE, where we're using the form of the SEIRD equations, right? So in this equation, you have susceptible individuals become exposed individuals become infected individuals either recover or die, right? Very simple ODE process. A lot of people use these models in epidemic models, right? What we're basically saying is that the thing should be epidemic-like, right? But now when you build an SEIRD model, one of the things that's one of the hardest things to actually model is what is the rate of exposure to COVID-19, right? Because the rate of exposure in Sweden, Sweden did not have a lockdown versus Wuhan, China, which had some crazy form of a lockdown versus, the United States was even crazier because it could depend on exactly what state you're in or what city you're in, right? Like, how do you even model exposure if it depends on all these different factors? It's kind of hard to just write down like, oh yeah, this quadratic polynomial is a perfect fit, right? Like you're not going to come up with that analytically. So the rate of exposure to COVID-19 as a function of how many people are susceptible, infected, and recovered, right? It's a very political thing, right? That where, if more people are infected, then you get lockdowns and yada yada yada. This rate of exposure is a very weird thing. It's a very non-linear feature, and so to just try to write down a term would be impossible. So what we do is we don't even try. We just say, hey, there's a neural network that covers this exposure term, and we don't know how to model this, but here's our model, right? And if we take this and we say, okay, we now fit the neural network against the data that we have in the first 21 days, we go from something that is able to learn from the same data and extrapolate to a much better extrapolation, right? Now, I want to highlight a few things about this model because a lot of people, kind of just look at this and they just go, okay, well, okay, so the idea is that you just, put some ODE stuff with it, and so therefore it's more epidemic-like, and so therefore it works better. But there's actually a lot more mathematical stuff going on here, right? So let me actually dig into this a little bit. First of all, I highlighted the idea of heterogeneous data, right? So one of the things that you can get in terms of an epidemic is heterogeneous data. So you might ask the question here, like how do you get this parameter mu? How do you get this parameter gamma? How do you get this parameter d? Right? It turns out that with epidemics, you get these parameters not by looking at your time series at all, right? So mu is the fraction of individuals who die or recover instead of die, right? Um, which, what is the recovery rate of the disease you can get from the hospital data, right? You don't need to use the time series. It's just, okay, that's what percentage of people recover versus die. And then there's other piece rates inside of here, which are all, they're equivalently weighted to each other once you non-dimensionalize this type of model, right? And so and so one of the key things about using a model formulation is precisely the fact that you can write down things that have these parameters, where these parameters can be guessed or kind of be in the right ballpark by using a data set that is separate from the data set that you train on, right? It's the idea of using the heterogeneous data. I think that is kind of completely ignored in, academic practice with scientific machine learning, but is probably one of the most practical things about using it in reality. That yeah, you can make your actual data set, be useful, more useful because a lot of these other pieces can be put in the right ballpark, fixed, and you used other things for fitting, right? So one thing here is that the universal ODE form is able to make use of this heterogeneous data that you naturally have in most scientific contexts quite well, right? I think one of the other things to then highlight is that you can think about this as, okay, this is a very epidemic like model, and I train this neural network, and so therefore on an epidemic type data, it tends to do better, right? That's a very hand wavy type of way to explain it. But a non-hand wavy way to explain that this should be better is to think about it as function spaces, right? So remember, in this first version, we said, let the neural network be any possible function. We find one function and then we extrapolate, right? In this case, now we're saying the neural network, again, the neural network can be any possible function, right? But the solution to this set of ODEs is now what our approximator is, right? It is not a universal approximator, right? The neural network is a universal approximator, but we have an approximator something to do with S, E, I, R, and D time series, right? But what are the properties of these S, E, I, R, and D time series? Well, if you notice, because there's a minus here, plus here, minus here, plus here, yada, 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 and a bit of ODE theory, right? You know that actually the one of the things that you can guarantee from the solution is actually that S plus E plus I plus R plus D is a constant, right? Because any motion from S to E is covered, and so the any negative you have the exact plus on another side. There can be numerical errors, of course, but this is something I would then guarantee, say in chemical reaction theory, that you'd have conservation laws imposed in this, where here it'd be the conservation of the number of people, right? People in your model cannot appear or disappear. That wasn't necessarily true in the pure neural network, right? Because the function that you learn for S, I, and R, it could be potentially any ODE, right? But here, by moving into this form, we actually have that, the number of people in our model must be conserved, right? And that's a conserved quantity by the formulation of the model. For every choice of parameters that you put here, for every possible function that you put here, if the equivalent function is actually plus on this side and negative on this side, then for all possible functions, you have the conservation law. That's a provable statement, and that means that this form of the model guarantees a conservation law, but also guarantees some other things, right? So if you take the neural network output and you say to use the absolute value on it, so that way this is always a positive quantity. So the neural network is a universal approximator to positive functions, positive continuous functions. Um, and then what you can actually guarantee then is that, if this is a positive function, then actually you can actually guarantee that S is going to have a peak. And if S has a peak, then E has a peak and I has a peak. And so therefore, this is a universal approximator of models that for which have a peak in the number of exposed and infected people, right? Um, so I mean, you can start to see that you get a lot of these properties where you just say, okay, it's not just that it's epidemic-like, right? What we're doing when we do this is we're building an architecture that is effectively saying, I want to find a universal approximator for S, the number of people who are susceptible, infected, and recovered. But I want this universal approximator to be in the space of functions such that I will have, the infection count will have one peak. Sometime early in the pandemic, and that the number of people within the model is conserved. Yeah, all these different properties actually just follow for free by putting into this ODE form. And if you think about it like that, right, what we did before was he said, okay, in the space of all possible functions that fit the data, choose one randomly and see how well it does, right? Now we're saying on the subset of functions that actually match all the properties of an epidemic, choose one of the functions out of there, and how well does it do? You should at least be able to see like, oh, I have a much higher probability of choosing a function that will extrapolate well, right? Not necessarily going to guarantee that you will, right? I think that actually proving a guarantee might not be possible because you can always have neural networks do weird things, but you have a much higher probability that from the smaller set of functions, for which the approximations are correct, right? In the smaller subset of functions, if the true function lives in the subset, instead of going from the larger set, then grabbing from the subset will increase your probability of getting a relatively good prediction, right? So that's a much more mathematical way to think about what's going on here. And then once you have it in a mechanistic form, there's all sorts of things that you can do, right? So you can, for example, perform a symbolic regression on the input-out behaviors of the neural network, then be able to re-represent it back down to like a simple form where you say, okay, this was a function of S, I, and R. But oh, hey, look, actually this equation that we get out of it when we sparsify it is only a function of S and I, which then gives me a mechanistic prediction, which is that, the amount of exposure to COVID-19 is not a function of the number of people who've recovered, because people who've recovered are not spreading the disease, right? So that's a hypothesis you could get directly from reading off the sparse regression. And one of the other things that you tend to see is that the sparse regression tends to improve the generalizability. The reason is because once you do some regression into a simpler form, you tend to be cutting off the tail behavior of the neural network, and a lot of the tail behavior tends to not be very useful, right? You can actually use some ideas from polynomial extrapolation theory that basically says that extrapolating with lower order polynomials can be much better as you leave the domain that has been fit, right? So there's certain ideas you can do here. We don't have a full proof for why this always happens, but it is kind of a nice thing that you can kind of see that once you have this sparsification, you do get better generalizability. Um, but then this is really just showing you all the steps of the universal approximator differential equation, right? You write down all the equations that you know, you then fit this neural network against the pieces of data to learn unknown relationships, and then you sparsify it down to get predictions of the given model, right? And each of these steps of the process is putting in effectively a different kind of information to improve this prediction aspect. So, when we do a lot of scientific machine learning using this approach, and I know this is kind of getting some popularity. It is very very different from the approaches of physics-informed neural networks and neural operators because it's using the infrastructure of things like existing differential equation solvers. And, I'll show in a little bit at the end what you have to do to modify equation solvers to make this work. But one of the other things that you're effectively using then is not just the knowledge of the equations that you know, but also the prior knowledge about numerical analysis, higher order differential equation solvers. All of this is coming into play when you're using this pipeline. Um, so one of the things they might want to ask then that I didn't go through with this, this ex first starting example always takes a bit of time, but one of the things it doesn't highlight is this idea of, well, what if I poured in more model? What if I poured in less data, right? So here I only said that this one piece is a neural network. I justified it in terms of like, okay, the exposure is like the hardest thing to model, so throw it out. But okay, you might want to say, well, what if I don't believe in this term? What if I don't believe in the, what if I don't believe in, each of these little bits you could just, kind of describe and go, okay, okay, okay. Like, you could make more and more of it be a neural network, right? There isn't really a bound on what it is. They say, what is the part that I know, right? Different people, you might have different justifications or uncertainty on different amounts of it, right? And so the real question is, does this relationship work in a continuous sense, right? If I made the neural network a little bit bigger, does that mean I need a little bit more data in some sense? And so we end up having there's a set of papers that do this in the context of epidemic models that basically shows this continuous behavior, right? And so, here in the plot, I'm showing you like one end, which is like, okay, I have most of the model and I have a little bit of neural network, and then neural ODE is all neural network, right? But what you really see is that you have this continuum where as the neural network is trying to do more and more and more and more, then learning from the same start amount of data will give you better predictions with the one that has more prior model. That should be obvious. I mean, you should have been able to guess that that would be the behavior, right? But, we have the right, if you're looking for, the right, what's the word, validations to be able to show that this idea should work out. We do have done these validations to basically show that, yeah, as you pour in more model, you do not need less data, right? And so, now all this stuff with scientific machine learning, with the universal differential equations, we've been able to get it so that way it's rather, stable and robust and solid and, a standard tool, right? And so here, for example, is a nice example that comes from folks that worked on astrophysics. Let me just kind of pull up the example here. So if you go to da, 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 if you go to docs.sciml.ai, and you go to the SciML showcase, right, you'll actually see that this example is here, discovering relativistic corrections of binary black hole dynamics. So if you ever thought like, sorry, I'm still a little sick. But if you ever thought, I want to just give Julia a try, I want to kind of learn how to do some of this stuff. Um, here's a nice example of give me one second. I'm a little sick here. Yeah, sorry about that. Yeah, so if you ever thought like, oh, I want to maybe learn a bit of Julia, so here's a nice example where what you do is you start with Newtonian mechanics as your prior knowledge, and then you use the data from a binary black hole system, right? So black holes are rather large, so they have relativistic effects on their dynamics. So you use the data from the binary black hole system to learn how to perturb from the motion of a two-body system from Newtonian physics to the Einsteinian corrected physics, right? And so this is just a tutorial, you can pick it up, you can run with it. And it shows you all the little tricks and tips for being able to do this. And you can actually see then that so here it is in terms of phase space, right? You can see that the original Newtonian trajectory is ellipse, right? That's just the standard solution to Newton's law of gravity, two-body problem, right? That you get an ellipse as your solution. But the moment that you turn this into a problem where you have gravitational or general relativity, right? Then you have the relativistic effects turns this into a Lysergy pattern, right? That's like your standard result, which is the result that you get with the perihelion of Mercury, right? And so And so this is actually kind of the recapitulation of that kind of exact problem using the LIGO black hole data. So you remember that the LIGO black hole or LIGO gravitational wave experiment was a first detection of gravitational waves, and it actually used the a blind binary black hole system. So they've actually set this up as we actually took this as an example from their paper where they say, okay, like let's use this real case, yada yada yada. You assume Newtonian physics in a rotating frame, and you learn the relative physics corrections, right? We just have this now this is just a standard documentation example of, learn relativity from Newtonian physics plus data, right? So I mostly highlight that just to be able to show you that, this is not something that's like, at one point it was very greenfield of like, like, oh, you have to learn a bit of the code and such, and you have to dig into it. But at this point, it's actually pretty standard, right? It's like, being able to do the example that I showed before and this example. These are now tutorials where you can copy paste, run it, and then, you teach an undergrad how to do it in their first year of undergrad, right? The scientific machine learning has really kind of progressed to that point now. So, I want to kind of go into other topics. So I just want to kind of highlight that, you might be asking, okay, in epidemics and then also in black holes, well, what about other examples, right? We have examples in earthquake safe buildings and da, 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 da. I give a whole talk on a lot of academic types of nice use cases of universal differential equations. So I'd say go over to that YouTube talk where I talk about how people have used UDEs to be able to correct things like earthquake safe, models of earthquake safe buildings, and use that to be able to design a better building and all these sorts of experiments. But going to move on to the next point. So if you want to hear more on that
Just one
category,
question.
yep,
If
yep.
I may. Uh, have you tried the chaotic system or
Um, let's see. Do I have the stuff on chaotic systems inside of this talk? Da, 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 da. Um. So okay, I have some notes somewhere on the back material with the chaotic system. So okay, so if you're going to do universal differential equations or any differentiable physics on chaotic systems, you do have to take into account the fact that automatic differentiation is not convergent on a chaotic system. Right here. Yeah, so if you are going to do this on chaotic systems, you have to take into account the fact that automatic differentiation of your solver to be able to do the training process is not convergent to the correct derivative, or not convergent to any derivative at all, really, for a chaotic system, right? So you always kind of think like, okay, if I'm going to run automatic differentiation on a solver, it's Euler's method, yada yada, and it'll converge to the right gradient. The second half of my talk is all about convergence of gradients of the correct solution. But I'll kind of this part I kind of cut out, so I'll kind of mention it now. What turns out to be going on here is that if you have a chaotic system, your original trajectory is actually incorrect, right? Because you have a exponential divergence in the tangent space, and that exponential divergence is the Lyapunov coefficient, right? It turns out that actually your automatic differentiation, well, the automatic differentiation is calculating using the tangent space, and so you can actually use that to be able to prove that any automatic differentiation algorithm on a chaotic system is actually going to give you a non-convergent gradient prediction, right? And so here, for example, with forward mode automatic differentiation on the Lorentz equation, it says minus 50,000 is a gradient with respect to the average of z with respect to one parameter, right? Of course, it's not actually minus 50,000. And if you actually run it longer and longer and longer, it actually just diverges up to infinity. And the rate at which this error growth happens is actually the Lyapunov coefficient. It's exactly the property of the Lyapunov coefficient is exactly the same property that gives you the non-convergence of automatic differentiation. So we have done something to this. You can actually kind of see that there's a blog post that we wrote on this, which is how do you correct these gradients? And inside of, and actually, yeah, here's a slide here that shows you can fit UDEs and such on chaotic systems using a special tool that only exists within the library that we haven't published yet. So, I'm kind of showing you some early stage stuff here. But yeah, I think that we have a tutorial that's on how to use sensitivity analysis for chaotic systems. That you have to do something called a shadowing approach. And so basically what you have to do is you just have to say for a chaotic system, you end up only having probabilistic quantities. And so the derivative does not exist in the classical sense. But if the system is ergodic, then you can actually calculate the derivative with respect to ergodic quantities. So for example, in the Lorentz equation, you can say what is the average value of z as z goes to infinity, as the amount of time goes to infinity, right? The derivative, basically what you're saying is like there are these properties that are defined by the attractor that the solution lives on, and the attractor itself will move as you change the parameters, and those have well-defined derivatives. And you can change the way that you do your automatic differentiation to calculate the derivatives with respect to ergodic quantities directly. It's using something that's known as shadow adjoints, and that's like a whole topic of its own. But yeah, so we do have some things to be able to show how to do this on chaotic systems, but it definitely requires a completely different set of machinery. Very, very good question. And did that cover what you wanted to hear?
Yes, thank you.
All right. Yeah. So I mean, so that highlights, this fact that, and I'm going to go into the training as the second part of this here, but I think that the key idea is that, if you can stick a neural network in things, and if you can train the neural network, you're good. But definitely where what I'm really have glossed over in this first set of slides is, can you actually train that neural network? In chaotic systems, you might have an issue with discrete stochasticity. You might have an issue. There's a lot of different cases where you might have to do a lot of interesting math to be able to make the neural network train. But the model formulation idea of, you can take any kind of simulation process and replace part of it with the neural network. It's a general simulation. It's a general idea you can apply to lots of different types of modeling as long as you can train the neural networks, right? And so this talk kind of goes into a bit more detail on how to do this accurately and efficiently on a lot of different real cases, right? But one of the things I want to kind of highlight before I go into the training techniques is, that you can use this idea to be able to use prior known structure that is not just in terms of equations, right? Because I think a lot of people get the wrong idea where you go, okay, well, I don't know all the equations in my case, so I can't really use this idea as much, right? Turns out that that's not really the case. So here's one way to highlight it, right? So again, we go to something simple like an epidemic model. And so in this epidemic model, you say like, oh, S goes to I goes to R, and I goes to D, right? So susceptible people become infected people recover, infected people can die. What if you didn't know any of these equations, right? Let's say you didn't know any of the equations in this epidemic case. Well, you might still know something about how the interactions between terms, right? So for example, S can go to I, but S does not directly ever go to R. S goes through I to go to R, right? You have to become infected before you ever recover. That is structural information that we might know about the system, and can we input code that somewhere that must be true in order to make our prediction method a bit better? Turns out you can. So, let's just give this a try using like this 3 neural networks, right? So each neural network is in a universal function approximator, right? But what I want to do is I want to say, okay, make all of them positive approximators, so just take the absolute value of them, and all we do is you just say, whatever minus this one here, plus goes here, minus this one goes here, minus this one goes here. Notice that this is encoding the same structure, right? This is saying that, S goes to I goes to R, and I goes to D. And because of the way we set this up, we also have all the conservation laws, right? So S plus I plus R plus D is constant, right? So we defined our system in such a way where we might know 0 of the equations, but we still actually have the flow of the equations in general, right? S is always decreasing. I has a peak because this is decreasing, right? You still have a lot of these epidemic properties, right? S is decreasing, I has a peak, and the conservation of people is all imposed without even writing down a single known equation, right? And so this shows that, if you use this kind of model formulation smartly, you can do a lot of nice things. And what we show is that, for example, when doing this and you check it against Cindy, right, you're able to effectively show that, Cindy requires learning the full system from scratch from data, whereas this is imposing some prior knowledge, and then you could do symbolic regression on the neural networks, right? What we show is that you can do this much more data efficiently. This is much more data efficient than just doing direct Cindy, because effectively we're of the prior knowledge we've imposed through this, right? So this is just a nice example to show you that, there's many different ways to think about how to use the prior structure that is well beyond just like defining some ODEs. Of course, the simplest one to explain is that you define some ODEs, but I would keep this one in mind to be able to say, hey, I can use multiple neural networks and I can use them in specific ways. Another nice example of this is with partial differential equations, right? So if you have a reaction diffusion equation, you can have an R2 to R2 neural network, say that is trying to learn what the reaction term is. So instead of trying to learn an entire spatiotemporal process, you're just trying to say, I'm just trying to learn an R2 to R2 function for what is a rate of chemical reaction in every single point in space. If you think about doing the semi-discretization, say the finite difference method, you put the same function everywhere in space. And so instead of using, a function that is like taking in time and all points in space and giving out this giant output, there's now a really tiny function that is repeated everywhere in space. And through that repetition, you've effectively multiplied your data by n squared to be able to train this function, right? Because now once you said like the chemical reaction must be the same everywhere in space, then you just say, okay, well, this function must be preserved. What is that function, right? And you've given yourself a lot more data by using this transformation. And we're able to show then that even with the small amount of data, you're able to learn how to predict to the future events in a way where if this was just a pure LSTM, there's no way it would ever be able to predict from this. It goes down to here, right? But again, if you're actually learning what the true chemical reactions are, then this prediction is much simpler, right? And so, this kind of idea of like if I choose the neural networks in the right way and use the right structure in my equations, I can get a lot more out of it. And even in this context, we're now starting to say I have a partial differential equation with spatiotemporal data, yada, yada, yada. You can still do the symbolic regression to be able to say, okay, I've used all this prior information in code structure, but I still want to learn what the equations are, right? I use the neural network as a continuous approximation to all possible functions. And once I have that continuous approximation, you can do the symbolic regression on the neural network. And you can use that to be able to then predict what the actual equations are. Now, what we're able to show, for example, in this context, you can dig into the paper for more details. What we were able to show in this context, though, is that even though you might not be able to learn the exact equations, you might be able to get something that has very similar properties. In fact, what we're able to show is that the learned equations that we're able to get out of this actually are very close in terms of the second order Taylor series expansion, right? So yeah, you won't be able to always learn exactly the right equation. And as you get to this is now a chemical reactor in 2 dimensions, yada, yada, yada. Getting the exact equation is a very hard, difficult thing to ask for. But, being able to get something that is a representative equation through this process with very minimal data is something that is able to be done. And we were able to demonstrate that, right? So I think the thing to get across more, though, is that use as much of the structure as possible. That structure might be in form of the equations, or it might be in the form of the ways that you share properties across space and time, like, for example, in PD discretizations. Now, yeah, hold on one second again. It's still a little bit. So a nice use case that we had of this is in the context of pharmacology, right? So in the introduction, it mentioned that one of the things I do is pharmacometrics. This is how we introduce pharmacometrics to people who do pharmacometrics, which is that what you're trying to do is you're trying to find how the same drug might act differently on different folks in the population. But in terms of people who do a lot of math, here's what it looks like in practice. You have what's known as a nonlinear mixed effects model, where you have these things called covariates, which are things that are easy to measure when someone enters a clinic. Think like weight or sex. You then have a model that collates those covariates into parameters, and those are then the parameters of some ordinary differential equation, right? So the purpose of a nonlinear mixed effects model is to be able to learn from the covariates like weight and sex how different people will have different internal drug dynamics that are different. So for example, how I might metabolize the drug faster than you, and so therefore we might need to take into account things like weight or sex in terms of how we figure out how to dose people to do the optimal dosing, right? And so nonlinear mixed effects is a problem where I mean, every single pill bottle that you've ever used, every pill you've ever used, has had to be approved through the FDA by using nonlinear mixed effects modeling. In fact, and again, one of my company hats here is I developed one of the software that's widely used. There's kind of two softwares that's used in the market. One of them is Pumas, and so a lot of the regulatory aspects of how do you do drug dosing and such. And a lot of the FDA filings are actually using the software I had created for nonlinear mixed effects. One nice example of this is the COVID-19 vaccine from Moderna was done, and it had this record time to market because of some of this nonlinear mixed effects tools that we had created in Julia, right? And that's just like a quick background on like, there's this other thing that I do that's industry specific because of this, right? But one of the interesting things that one the reason why I bring this up is that, when we're talking with, say, Moderna and their clinical pharmacology team and trying to get, the fastest vaccine out for very obvious reasons, right? One of the interesting things that came up was that, the time to do this analysis is not actually driven as much by, how to do this analysis. We spent years making sure that that was robust and stable and fast. But the real question is, how do you come up with the equations for these models, right? You can have some capsule specific behaviors where you say like, okay, or the clearance of this drug is dependent on some function of the weight, right? You might know that you might know that that's going to be true for some antifungals and such. For an mRNA, we were kind of blind, right? And so it turned out that one of the big questions in the context of pharmacometrics was, how do you come up with what these functional forms would be faster? How do you get the first guess so that when we can go to the clinic, we could do much more refined experiments to be able to come up with these equations faster, right? And it turns out that one hat I was working on Pumas, the other hat I was at MIT building this scientific machine learning and universal differential equations tools, and it turns out that they had the perfect fit here, right? Where in this context in pharmacometrics, you might have a neural network stand-in for some of these functions, and now the actual fitting process is completely different. You need to make use of something that's a maximum likelihood with respect to the Laplace, yada 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 yada. I'm not going to go into details. This is not a clinical NLME talk, right? But the same idea happens, right? Where you would have had to find fixed effects and random effects. And so you'd have these kind of parameters of your model. If you make the weights of your neural network be fixed effects within this model, then it ends up being something similar to being able to find equations you didn't know about. And then you can do the sparse regression process to be able to predict what those equations would be. And those predicted equations are then useful in being able to write down like, oh, this is what I believe the equation is. And you can use that as a tool to then go back to the lab and prove that you have a weight dependent effect, or prove that you have a sex dependent effect, right? In order to do this for the actual clinical trial, to do this in the FDA filing, you have to have some alternative proof for the equation forms. But this actually helps you really get make a first guess on what all of those equations are. And so you know what experiments to run. And so this is, and so you can think about like this scientific machine learning is not just trying to just do a straight automation of scientists. And I think, yeah, a lot of people throw out a lot of crazy, AI is going to take over the world kind of thing. This is, if you think about it in a practical sense, the scientists can still be in the loop here. But it's just the speed at which you get a correct model could be a lot faster and more directed rather than guess and check. And, the way that you did this before is you would try to read, 15,000 papers, and one of them says, hey, yes, capsules which use this chemistry have a weight dependent effect. This was found in 1997. And so therefore I have this equation right here, right? Instead of trying to figure out what all the equations should be by doing that, you get a guess of what the equations are. And then you just go, well, can I find something in the literature that matches this, right? And you can go back to literature and just see, has anyone found that cesium has a weight dependent effect? Boom, you type that in and you get a pretty quick direct hit, right? So it's I think the way to think about it is that you get a much more directed kind of way to be able to go across the model construction process, and that's probably in terms of an industrial context, that's probably the more useful thing, right? I know that in an academic setting, people are going to be asking questions like, oh, how close do you extrapolate versus one method to the another, right? It turns out that nobody actually really cares about any of that. Like, sure, that's how you get a NeurIPS paper, but what people actually care about is what is the speed at which I can get a model built that I can actually then verify through other means. And it turns out that the universal differential equation approach is very good at doing real world things like that. Just this kind of highlight, that's just one way to be able to understand, some of the ways that we're using EDs, right? And so I do want to kind of put an industrial hat on with that, and with my VP of modeling simulation thing with the Julia Hub, and now it's a question of, how are we transitioning these kinds of tools to be something that everyone can make use of, right? So what we're doing then is so what we're doing is we're taking these kind of techniques that are known as acausal component-based modeling techniques. I don't know if you're familiar with things like Modelica or GPROMs. Like these are kind of software where you can have models of tools, like for example, a model resistor, a model of a inductor, and then you can just connect them together and it generates the composite equations. What we're doing right now with Julia Hub is we're building out something called Julia Sim, where you have these pre-built components for things like batteries and HVAC systems and a lot of digital twin components. But then what we're doing is we're making it so that way you can embed neural networks as to be able to say, okay, I actually don't know how this piece works, right? I may know a lot about my battery, but I don't know a lot about the battery draw from the perception system in my car, right? And so you can have a full, complete model, this two-dimensional partial differential equation developed over 5 years of the battery system, connect that with, something that five people have been working on and for this active suspension system, right? You have this whole very correct physics model, but then you just say in one part, you just say, hey, you know what? Like the HVAC system used the ideal gas law for the way that it did its refrigerant properties, but it's not taking into account things like two-phase flow, which will have with so for example, if you run your HVAC system, it will have a phase change from being liquid to gaseous and all at a certain point, right? And that two-phase flow will completely change the properties of how you can of the efficiency of the system. So I mean, you can start to say like, hey, I want to be able to connect all these things from a component library, but I want to be able to put a neural network right here to correct it and do the UDE thing in general, right? So we've been building out a full graphical user interface system that has been able to kind of take what I described before and make it so that way it's very easy to build a complete, non-toy model of things like cars, automobiles, airplanes, and such, and then be able to use that along with the and scientific machine learning techniques. Now, this is more of an academic talk, so I'm not going to go into all the details on all that, but I thought that just kind of like to show, if you're familiar with things like Simulink, this is how that space is really evolving now to be able to take into account things like scientific machine learning. Um, One nice example that we have of this is with the Williams racing team. So what you see here on the right is that so they have a speed over ground sensor. So the speed over ground sensor is actually seeing what the orientation of the car is as it goes around the field. And what they're using before is they're just had straight measurements from the SOG to predict what the car's orientation was, and so they try to use this in the race computer to predict, like, okay, when they try to tell the driver on headphones, be able to say, hey, you keep on taking this turn at 45 degrees, you should be doing this at 48 degrees, right? From the test laps, they kind of know this information, but they're trying to then see, okay, what is the orientation the car is actually hitting the current turns, right? The sensors on the car are supposed to do this, but the sensors are bad because they're trying to be aerodynamic, right? And so what then they did was they said, okay, well, we're going to calibrate the sensors just using the data and stick it into a neural network. And we said, no, 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 no. Like you don't need to just have predict the orientation of the car directly from the sensors, right? You know how a car works, right? So details, right? Proprietary details. I'm skipping over. But what we did was we built out a semi-small vehicle dynamics model of the car and relating it to the speed over ground sensor to be able to correct for the differences that the car model doesn't have. One major effect, for example, is the wheel skidding that happens as you go around the edges. There's a lot of wheel skidding you have to take into account because the Formula One cars are going so fast that they're not going to actually match the true acceleration that you had because of these skidding effects and the frictions there and such. So what you can do is you can do a model of the car and you can say, well, I need to have corrections for this, and these corrections should come from the speed over ground sensor, right? And you can see that the original one that they had deployed is the one on the right here, versus the one we have over here, which has a vehicle dynamics model in there. And you can see that, the one that with the vehicle dynamics and infused one is just a much better prediction and ends up being much better for being able to know the true orientation of the car and then give live feedback to the driver. Um, I like this example a lot because it's a showcase that scientific machine learning is cool because, actually with what we did with Julia Hub, you can actually see our logo on there. So our logo is on the Williams racing car. And I did actually go clubbing with George Russell before he went over to the Mercedes team. So, this shows that math is cool, but also like scientific machine learning is finding real use cases in a lot of these, hardcore industrial contexts. Yeah, so there's some other use cases here with car catapults and such, but I want to make sure that I get to the final piece here, which is that how do we get to the training? I'm a little bit behind on the schedule that I wanted to do, but I want to I want to kind of talk about this a little bit. So I kind of skipped over entirely how we train these neural networks. Effectively, what we do though is we say, okay, let's say we have this case where we have a 3D PDE that we want to approximate with a 1D PDE. So I want to make this 1D PDE fit this data. So that way, for how temperature moves up and down an ocean column. What you do is you basically, the first thing that you can think about is, well, if I want to make this differential equation be correct, I can use the time derivative of this data, and I can fit a neural network to the correction of the time derivative of the function. And if you do that, then what you find is that you have a drift over time, all right? Because if you think about this from a control theory standpoint, if you make your neural network correct the derivative, and then your loss function is only about correcting the derivative, then it's almost as though you did a control theoretic thing of only making sure that you correct derivatives, which one of the consequences in control theory of only doing derivative control is that you always get a drift in the solution over time. And the way that you correct for that is that you make sure that you have a corrective element on the integral, right? This is why you have PID controllers. The integral controller is actually required so that way you get the long-term stability properties, right? What that means in terms of the solving process here is that the right way to be able to train these neural networks is you define loss functions where you solve the differential equation and then you check the solution of the differential equation against the solution data, and that's the kind of loss function that you need, right? You can find that that gives you about 2 to 3 orders of magnitude better fits. And so the reason why this is important then is that it means that in order to do this neural network training, the real thing that you need to be able to do is you need to be able to define loss functions that have your differential equation solver inside of there and be able to differentiate the solving process, right? And this is where we get to differentiable simulation. Now, you might just think that, okay, I have a simulator. I have like Euler's method or something, and automatic differentiation exists. So I just call automatic differentiation on it. So therefore, there you go, right? You write this loss function, you call automatic differentiation on it, and I'm good, right? I want to show you that, there's a lot more math to be done here. So I do have a very big review article that goes into detail on this. I'd love, you check it out. Differentiable programming for differential equations. We go into all these different ways to be able to calculate derivatives. And many of these are all what you would call the adjoint method or automatic differentiation. It turns out that when you say the adjoint method, there are many different ways to actually compute it, and they have very different stability properties and very different performance properties and memory properties and such. So being able to really distinguish and make the language clear, we've come up with different names and been able to classify the whole space of methods here. But let me kind of just highlight that calculating derivatives correctly can be actually pretty hard, right? So here, for example, is one case from the neural ordinary differential equations paper, the original neural ODE paper, which says one way to calculate the derivative of an ODE is you solve this forwards, and then because u prime equals minus f goes on the same trajectory going backwards, you can solve this ODE in reverse, and that will give you the derivative as one of the terms. Beautiful form. Wasn't actually all that novel. We kind of knew this kind of technique, but why did no one ever implement it in software before? Well, there's a reason why no one ever implemented it like the neural ODE paper before. It's because if it turns out that reversibility is not necessarily a guaranteed property, right? In terms of an ODE, theoretically, if you solve this ODE, then in theory, this ODE will give you the same problem in reverse. But it turns out that for once you discretize this ODE, you do not actually get that property in general, right? One nice example to be able to explain this is the advection equation. If you know from your standard linear PDE course, right, you can either discretize this in terms of the upwind or the downwind solution. And if you choose the wrong one, then you actually get unconditional instability, right? So basically, if the wave is moving to the right, then you better use the data point from the left, because that point from the left is going to be the analytical solution for what the value is in the near future, right? So you basically just need to if something is translating from left to right, you better have that the left value is in your solution. If the left value never shows up in your solution, then there's no way you'll ever get the right answer, right? It's you can show this by von Neumann stability analysis, but that's like the obvious way to explain it. Now, why is this relevant? Well, if you think about the way that they calculate the adjoint here, you'll instantly see what goes on in this equation, right? Because if you solve the advection equation going forwards, then you say for your adjoint method, you want to solve that same version with minus going in reverse, right? What effectively happens is that the wave is going in the opposite direction. And so you'd have to actually, so then in the reverse direction, the backwards method is then unconditionally stable, and the upwinding is unconditionally unstable, which means that which means that you get unconditional instability in the solve of this ODE right here, right? And by von Neumann analysis, you can prove for that for all delta x and for all delta t, you do not converge to the right solution. That's very simple from your linear PDE theory to get this. And this is actually, if you use, like, for example, torch diffie-q inside of the PyTorch library for neural ODEs, this is why it gives incorrect derivatives, because it's using a method that is provably unconditionally unstable, right? In this paper, stiff nor ordinary differential equations, we then go into a lot of detail to be able to show that it's a property that's not, this reversibility is a property that's based off of the Lipschitz constant associated with the function. And as the Lipschitz constant of the function grows, you get an exponential growth in the error in the method, which then goes to, 10 to the 20th, but by the time lambda is about 50, right? So basically what this is saying is that, like, yes, you can calculate the adjoint with this, and if all of your examples are on non-stiff ODEs, like they did in their paper, then you'll be fine. But the moment that you get to a stiff ODE, then this method that you find in the PyTorch library is unconditionally unstable, and so you'll be able to find these examples for which the derivative is not converging to the right answer. Most of the times, I'll give you something like a nan or an infinite, because 10 to the 30th is not always representable, yada yada yada. But this shows you that there's a lot more math that you have to do then in order to, in the same way that you have to kind of do a lot of math on ODE solvers, where you say, yes, Euler's method does work for ODEs, but, it doesn't work for stiff ODEs and symplectic methods, yada, yada, yada. Just like there's a whole math for that, turns out that there's a whole math for how to calculate derivatives correctly. And another really nice example that might blow a few people's minds here is that, so here, let's take a test problem. Here's a linear ODE, right? On this linear ODE, what we do is we can show that, for example, with the Julia method, we can calculate with forward mode and reverse mode. You can see that we get derivatives of 1,1,0,1,3 minus and it turns out we can verify that these are the right answer to the derivative. Because this is a linear ODE, we can write down the analytical solution, get the right analytical derivative, right? If we didn't implement this in JAX, right? So you use the diffrax library from JAX, and then you do the same thing. You then ask for its derivative. What you find is that, backsolve adjoint, which is, again, this is the one that's unstable. But since this ODE is non-stiff and everything, as long as your tolerance is small enough, right? So you're too high of a tolerance, it won't be converged, but low enough a tolerance, you're fine. So this method and and finite differences converges to the correct derivative, right? But you actually see a funny thing. So here, this is the direct adjoint. So this is, hold on one second. So here you see that this is automatic differentiation in the code, or something using the recursive checkpointing adjoint, right? Now, if you put these options into the automatic differentiation engine or the direct adjoint, which is recommended as the most stable method, you actually see that you get the wrong answer here. In fact, it has about a 60% error. Yeah, what this is really showing is that, and this is just doing JAX's direct automatic differentiation of the ODE solver, right? So that might confuse you a little bit. You go, okay, automatic differentiation is accurate almost up to floating point, but obviously I just showed you an example right here where it actually has more than 60% error. I can actually construct this example so that way it has whatever percent error I want, right? Why is this the case, right? It turns out that calculating derivatives is hard, especially when you're doing it through a solver. And you can actually prove that automatic differentiation of a solver library, like an ODE solver, is not necessarily convergent. Yeah, do I not have the proof point in here? Well, so I have another talk that I give online that goes into the whole proof as to why this is the case. So yeah, I guess I knew that I'd run out of time here. But basically, you can basically what automatic differentiation is doing is that it's taking your original ODE solver and generating a new solver for a new ODE, right? So automatic differentiation is a code generation approach. So it'll take the solver for your original ODE and it'll generate a solver for a new ODE. It turns out that new ODE that is solving is an ODE that will give you the derivative, right? But then the way you can ask is the ODE that it's actually generating, is it actually stable, right? If you have a stable approach for your first ODE, and automatic differentiation is generating you a solver for the second ODE to calculate the derivative, is that ODE process that it's actually generating, is it actually a stable and convergent method for the derivative? And it turns out that that's not necessarily the case, right? What we do within the Julia library is we have some corrections to this, and this is a deep topic. There's another talk that I give on let me see if I can pull this up really quickly, and I can probably start taking some questions. But yeah, basically you can show in general you can prove why that not automatic differentiation is not always a convergent algorithm because of the way that it ends up working internally is building ODE solvers, and you aren't necessarily guaranteed that the new ODE solvers are going to be stable. So I'm going to probably be putting up an in-depth talk on that pretty soon. But yeah, basically this is the quick proof of it. So if you take an ODE U prime equals f of u, if you do this dual number arithmetic, which is equivalent to forward mode automatic differentiation, what you see is that you end up getting forward mode automatic differentiation turns Euler's method for a given equation into Euler's method for a new equation. This equation looks like this, right? And so then you have to ask yourself, is the stepping behavior for this equation guaranteed to be a stable stepping behavior for this equation, where the solution to the S part of it ends up being your derivative? And it turns out that it's not actually guaranteed. And so it's very easy to come up with counterexamples for which automatic differentiation of an ODE solver, such as Euler's method and whatnot, ends up giving you a non-convergent, incorrect answer. In fact, the example that I constructed there is kind of a fun one because as the tolerance goes to zero, you actually see that as you change the tolerance, you actually don't change the derivatives at all. The derivative is completely independent of the tolerance by construction here, because that tolerance, there's ways to be constructed so that way it's only taking into account the point here, right? So the point is that, where is all the math in the universal differential equations and such? All of the math is in calculating the derivatives correctly, because it turns out that just because you can write down something that is mathematically correct, it doesn't mean that you have something that is necessarily numerically stable or accurate. And so, naively just throwing automatic differentiation on a simulator is not necessarily convergent. And similarly, naively just using an adjoint method just because you've proven mathematically it works doesn't mean that it's necessarily a stable way to compute the derivatives. And so there's other talks that I give that go into a lot of detail on how do you make sure that you change the automatic differentiation process to be able to take all this into account. So I'll tell you that the Julia automatic differentiation libraries in the context of automatic differentiation actually breaks a standard property that your solver will not be unchanged in the context of automatic differentiation. We take different steps when we do the automatic differentiation process to account for the error of this solution process. So the adaptivity isn't just the error of your original process, but also that. And that's a requirement in order to actually fix this problem. But I want to just do that as a quick highlight to understand, like, why is this problem interesting? Why is it hard? All the mathematical details are in how you calculate derivatives. So I think that that's probably the last point I was going to get to, and I'm a little bit over time, but hopefully that's all fun and interesting. And I'd be happy to go into any more details that anyone wants to hear.
Great talk, Chris. Siddharth?
Yep. Hello, everyone. So thank you, like, once again, Chris, for giving this wonderful, amazing talk on a very diverse range of topics. So I'd like to just check with each one of the participants. If you have any questions, the floor is open to you, to each one of you. So please feel free to, like, unmute yourself and just ask a question if you have one. So so can you just so Chris, like, in case of participants, they don't have any question at this point, maybe I can just I have a question quickly
Yeah,
on the Formula One, the example that you showed. So
yeah, yeah.
you did mention that you're using, like, a vehicle dynamics model to basically, provide a feedback to the driver
Mhm,
when they are actually, driving there on the floor. So,
mhm.
so my question here was, like, so what kind of a measurement that you are basically taking each time from the vehicle, so as to update your vehicle dynamics model and
Yeah. So I rushed through it a little bit, but I can
sure.
talk about this in a little bit more detail, right? So the Williams Racing Team has this facility that's a bit outside Oxford, right? Where they basically have this control command center, which if you think about it, there's like 50 people. If you ever seen like the Apollo 11 movie, think about that, right? You have a bunch of people sitting at their computers with headphones on, right? And
Yes.
they're all messaging to this lead guy who's standing in front of a big screen. And the lead guy is actually the one who's talking to the driver live, right?
Yep.
And so, if you actually watch the Formula One race, right, you'll see that the drivers have these headphones on and they're talking to somebody, right? So what
Yep.
are they actually talking about, and why is scientific machine learning in here, right? So
Right.
what's going on is, for example, you have some people on the team which are, for example, they've done some trajectory optimization, right? So they say, for this car and for this kind of thing, for the models that we have, what is the optimal way to drive this track, right? And if you ever looked at, speed running games like Trackmania or something, like figuring out the right track trajectories is a very difficult problem. And so what they do is they find like, okay, you want to take an inside line here, outside line here, but they've also calculated like the optimal approach is at 44 degrees into this turn and all this kind of stuff, right?
Right.
But then during the actual race time, it's very difficult to actually know, is the driver hitting this at 44 degrees, or is he always taking that one too wide, right? So then they have the sensors on the car. So for example, this sensor is a speed over ground sensor. So it's a very thin sensor, right? It has to be very thin and terrible because so it needs to be aerodynamic. You can't really change the aerodynamics. So there's a very thin sensor on the bottom of the car that is basically just measuring how many bumps it's going over, right? Basically just finding that, as I'm measuring the ground, how fast do I think I am going, right? And it turns out that the speed over ground sensor is a very good sensor for potentially learning if you're doing, turns, right? Um, and so what they're trying to do then is they're trying to say from this sensor, can I find out what angle the driver is approaching the turns at? And then someone on their computer is supposed to be watching this and they're just going like, oh, and looking at the predicted the optimal trajectory and what they're actually doing. And then they see like, oh, the driver's just he's always taking this at 50 degrees. Like it should be 44. Like, he's losing so much time right here. And so he'll call it up to his head coach. And then the head coach will tell him in the next lap, hey, you keep on taking this turn too wide. Take it narrower next time. Take it narrow, about 6 degrees narrower, right? So this is like like when people watch Formula One, they know that like, oh, there's it's really run by the engineers, right? This is a very practical example of it is run by the engineers, and this is exactly what's going on, right? But one of the issues at the Williams Racing team, which before we started working with them, before actually George Russell got his first points a few months after we started working with them, right? If you remember this from 2022. Um,
Right.
but the one of the key issues is that if you aren't calibrating your sensor data correctly and everything, then it can be very difficult to know like, okay, like right here, if your sensor's off by like 10 degrees or something, it's going to be very difficult to be able to say like, oh, we know for a fact you keep on taking this too wide. Instead, all you can say is, yeah, well, the driver's doing something, and so you can't actually give him back good information to help him correct his driving during the test, right? So then, yeah, this is where then that scientific machine learning model is able to come into play by improving the sensor calibration, improving the prediction there, which then improves the ability to relay this information back over to the driver. So, we're still working with them on certain aspects about getting this into the race computer and such, but it's an ongoing process, and all the Formula One teams are in some form starting to make use of some elements of scientific machine learning in different aspects like this.
Thank you, Chris, for that explanation. But the reason why I asked you were like two reasons. The first one was that the model seemed to be like way too. I thought maybe it's very simple as well as it's very powerful at the same time because that's why it's able to mimic the movement of an F1 car or in a live stream format. So my question and another reason for the question was that when you're getting a feedback from the sensor, I believe there is always a delay that's attached to it. So
Mhm.
when a car is moving at, especially when it's not even a car, but rather it's an F1 car that's moving at maybe 5 or 6 times the speed of a normal car. So when you're like moving at such a high speed with such a high acceleration, I was just wondering whether you can account for that on an online setup.
Yeah,
So
I
that
mean, it is very difficult to account for an online
yeah,
seat,
yeah,
right?
yeah, yeah.
And you can't do it with just that one sensor, right? You have to have a lot of other sensors involved in it.
Right.
Yeah, so it becomes this multi-sensing kind of problem, which also has, again, like there's humans in the loop looking at the data coming off of the computer. So there's some human interpretation while they're watching the race, while they're watching this, while watching that. They're trying to guess like, okay, this is too wide, this is too thin. And this is just one person of the team, right? Then the different aspect of like, okay, should I switch out the tires, right? You have someone else looking at all the data for that on that screen, right? And so, there's all sorts sorts of different screens, and so you do have an human in the loop that's trying, that has a specialized. They have a specialized graphical user interface for their computer, which says like, window one is sensor one, window two is sensor two, window three is the speed over ground sensor, right? And for their computer, they're getting this live relay of information, and they have to then make a good guesstimate that they then give to the team lead, which then they act on. So yeah, and things are trying to get more and more automated as time goes on. But one interesting thing that happens a lot with Formula One I mean, there's two things that are interesting here. One of the things is that you're guaranteed that your sensors are bad because any good sensors, like, yeah, you can hang a camera outside of the computer and do this perfectly, but then
Right.
you lose all your dynamics. So you're guaranteed that your sensor's bad, right?
Yeah.
Um, and in fact, on one side, the people designing the car want you to use a smaller sensor every single time, and then of course, on the other side, you want to use a better sensor. So there's a lot of like back and forth between what to actually use in these vehicles and such. But then the other thing is that you also have no idea what the tires are. Remember that the tires, I believe that they're still given by a McLaren or something. Like there's a single manufacturer for all the tires, but and the tires are put onto the car during the race, right before the race, and they're taken off the car right after the race. And so actually the only information you have on how these tires work is from race data. And so and so you have to kind of do some live recalibration and stuff based off of all of this kind of information because there's a certain element in the car that is actually unknown. Um, but after a few races, you can start to learn some of the behaviors of the tires. But then, of course, you have to take into account the fact that you wear the tires really quickly as you are running these, and so it ends up being a very interesting kind of online scientific machine learning kind of problem. I'm saying what I can. There's a lot of
Right.
other
But,
proprietary
but
things in
thank you,
there,
thank you
but
for that
yeah.
all good overview. So, and also like you did mention about integration of PID to improve the prediction for a longer time period extrapolation rather. I may put it like that. So I think you did mention something about that. If you could just quickly if you could do a brief about that as well, that would be great.
Oh no, yeah. So what I was saying here is really just that the way that you do the training process inside of scientific machine learning, right?
Right.
You have to choose a loss function, right? So one thing that you can do is you can find data for this
Okay.
neural network, train the neural network, and then put it into your system. And what you're effectively doing is you're saying that my original equation is incorrect. I'm going
Right.
to use data about how the derivative is incorrect to
Right.
control for the derivative. And then I'm going to add this, you can almost think about if you think about UDEs from a control standpoint, this neural network is a controller that corrects for the derivative in that context, and then you're putting it back in, right?
Right.
But then you have all of the issues of derivative-based controls, right? If you had to choose one control that would improve the long-term convergence and such, right, it would be integral controls because that it always has a mean reverting process, right?
Right.
And the way to think about that then is that if you use the integral of your t, right, so you have this equation dou t, right? If you integrate this to get the actual temperature values, right, and you use the temperature values in your loss function, then you're training this neural network to actually make sure that the integral quantity is corrected by this, right? Now, and it turns out then that you can take this in all different ways, right? You can just say, well, can't you do an integral and a derivative at the same time? Yeah, you can have this loss function term and this loss function term. In fact, we have some papers that show that's a nice way to accelerate the fitting process, right? But so there's a lot of refinements you can do to this, right? But I think the main thing though is that the key point is that if you actually do want to do something that is a stable mean reverting kind of approach, you do actually have to do the fitting with the loss function of the loss function with the simulator inside of there, and that's how you get to differentiable simulation. It's probably a different way to get there from a lot of other people, but I come from this kind of industrial controls background where it's a fairly high level, nice way to be able to really describe that. Yeah, of course, just making sure your derivatives are correct. Of course, it's going to cause a drift. Like we know that from and so fitting this neural network and then sticking the simulator, it has the same exact issues there. I just think it's a very nice way to describe, that, why this would be the case.
So I think it takes into account all the properties of a PID controller and using like basically to reduce improve the convergence and like maybe improve the steady state error as well for your prediction. So
Yeah, yeah. And in fact, and then you can also come up with loss functions where you say, okay, I know that this is supposed to be the steady state, this is supposed to be the steady state. So, let me use those steady states as part of the fitting process. And we had another paper that was all about infinite time neural ODEs and how you can do fast adjoints on those and such. So, and you can mix the infinite time neural, you can mix the infinite time loss values with with the non-infinite time ones and all that. So, I mean, yeah, you can continue to just refine the loss functions that you have here, and the papers that we have at NeurIPS and such are kind of go into detail, right? That's all the stuff that you might want to go dig into if you're
sure.
interested in the math. But
Yeah, definitely. I mean, I'll just take a look into this. And thank you for this sharing this one. So thank you. Thank you.
mhm. Yeah, but
Thank
I think the high level though is that in general, putting the simulator inside the loss function is what you got to do, and then there's 50 different ways you want to make use of more, and then every single piece of more information you have, if you know the eigenvalues of your system should cause stability, well then maybe linearize your system around some points and show that the eigenvalues are negative. If I know things about steady states, you can use that. Anything that's structural about your system, you can encode into the loss function somehow. So.
Thank you, Chris. So I think if no one is having any questions, so I think we'd like to wrap the session for now. So I'd like to once again thank you, Chris, for
Yeah,
giving.
thank you for having me. Sorry, I was a little bit sick today, but hopefully you still
Sure.
got through
thank
it.
you, Chris, and for this wonderful talk. And hopefully, we will see more talks from you on, say, you said that automatic differentiation, right?
Oh yeah, yeah. I'm going to be doing a whole one on how automatic differentiation isn't necessarily convergent on the Gaussian equations, which I think is a fun topic because I hear everyone just say like, "Oh, I use automatic differentiation, so therefore I'm floating point close." It's so the easy way to describe why that's not the case is that that's the same reasoning behind ODE solvers that are ODE solvers that have a truncation error, but that is low, but is not necessarily stable, right? So a non-zero stable method, like the BDF method of seventh order has the property that it has a local truncation there that is O of delta t to the seventh power, but is non-stable. Similarly, you have this property that can happen with automatic differentiation, where just because you have that the error of every single operation is small, doesn't mean that when you add a bunch of steps that you have an error that's small as well, right? Because it could be growing in a way that is exponential, right? What you want your errors to be sometimes positive, sometimes negative, so they over time they cancel each other out, right? And so that's how you get the property stability. But then you have to ask a question of, if I do automatic differentiation on an arbitrary code, do I actually always get a stable calculation of the derivative? Or can I end up with something that is mathematically correct, but numerically unstable? And it turns out that you can. And there's a lot of really nice cases that come up in real world cases. And I think that kind of, yeah, that's the kind of fact that I think a lot of people kind of ignore right now. So I think it's a really nice thing to highlight. So hopefully that'll be the next video I do.
Okay, thanks.
Yeah, nice. Thanks for having me.